Hello, it's stat134, lecture 24. Last time we started section 9.4 on applications of the generalized likelihood ratio test to goodness of fit chi-squared test. You have, for example, a box with m types of tickets having some unknown probabilities. We draw n times with replacement from our box, and we observe counts x1, x2 up to xn, where the sum of these xi is n. And if the probability of the tickets in the box is p1 of theta up to pn theta, we expect to get counts np1 theta, np2 theta, and so on. And that's because these xi are binomial npi theta. We do a goodness of fit test. So that's the sum of the observed minus expected squared over expected. And this is a chi-squared with m minus 1 minus k degrees of freedom, where k is the dimension of the null space, which is basically the dimension of theta. A goodness of fit test explores how good your probability model fits your data. So today we're going to see why minus 2 log lambda is approximately the sum of these OI minus EI squared over EI. We know that minus 2 log lambda is approximately chi-squared with dimension omega minus dimension of little omega naught, and where omega is the sample space and omega naught's your null space. So the result will follow once we show the connection between minus 2 log lambda, which comes from the GLRT, and the Pearson chi-squared statistic. So we're actually not going to have time today for a test of homogeneity, but we'll start that next time. So today we're doing theory, section 9.5. The null hypothesis is that you have a multinomial distribution with cell probabilities p theta here, where p theta is p1 theta, p2 theta, and so on up to pm theta, where theta is theta 1 to theta k. So this is a k-dimensional subspace in Rk. And the alternative h1 is that we have a multinomial distribution with some different cell probabilities than in H0. So the sample space is the set of all non-negative numbers that sum to 1. In other words, P1 to PMs, all between 0 and 1 that sum to 1. And so omega is the max over theta in omega naught, likelihood of P1 theta to PM theta, over the max as our probabilities are any m tuple in our sample space. So we're running over all probabilities, and it's the likelihood of those probabilities. So the numerator, we're looking for whatever theta maximizes the likelihood, and that is exactly the MLE of theta. So the numerator is the likelihood of P1 theta hat to PM theta hat, and the denominator is the likelihood maximized by all the possible P1 to PMs, and that's by definition the likelihood of P1 hat to PM hat. So we have MLEs, but sort of different. One is MLE, an estimator of theta, and the other one's an estimator of the probabilities. So it turns out that the estimator of the probabilities is just xi over n, which completely makes sense. What else could it be? But if you want to see a rigorous proof of this involving Lagrange multipliers, see page 273. So xi is n p hat I, and note also that pi theta hat will converge to pi theta because theta hat converges to theta, and furthermore, if the null is true, then pi hat will converge to pi theta. So this is just consistency of MLE. So now the likelihood is just the formula for the multinomial distribution. So the numerator and denominator are just given by the multinomial distribution. The factorial stuff canceled, thank goodness, and we basically get a product of pi theta hat over pi hat to the xi. Xi is n pi hat by the boxed formula here, and so then minus 2 log lambda is minus 2 sum n pi hat log n pi theta hat over n p hat. So that's log ei over oi. And now it's starting to look pretty good. This summation, you could use that. To but instead it's common to use the Pearson chi-squared statistic, which is the sum of the ratio of oi minus ei squared over ei, and that just is a second term of a Taylor series approximation, which you can read about on page 342 in Rice. So that step is just an approximation by Taylor series. So that shows what we need. Now the minus 2 log lambda for large n, we saw that this is chi-squared dimension omega minus dimension omega naught. Omega is all m tuples of p1 to pm that's summed to 1, so that has dimension m minus 1, and omega naught is all k tuples theta 1 to theta k, where each theta I is some open interval in R, and so this has dimension k. So minus 2 log lambda converges to a chi-squared m minus 1 minus k degrees of freedom. Assumptions that go into the goodness of fit test is that we have one categorical variable. In other words, our box consists of a discrete number of tickets. We have independent observations. So we need this so that we have a multinomial distribution, and for that we're drawing with replacement. The outcomes are mutually exclusive, so every ticket is in exactly one cell. Again, so we have the multinomial distribution, and we require large n and no more than 20% of expected counts are less than 5. So that is because if we have small expected counts and a large n, then our p is likely small, and if p is small, then xi, which is binomial npi, will not be approximately normal. It will actually be Poisson, so it will be skewed to the left, and we need it to be normal because chi-squared is a normal theory. So we then ended with an example. So as part of a study on the selection of grand juries in Alameda, the education level of grand jurors was compared with the county distribution. So the trick here is that the number of jurors, that is our observed counts, but we don't get the expected counts directly. What we're given is P, the PIs, so we have to compute the expected counts, which is 62 times the PIs. So our null hypothesis is that P1 is 28.4, 48.5, 11.9, 11.2. H1 is that we have some other multinomial distribution. I've written out our observed and expected counts, and then we can just find our Pearson chi-square statistic. It's 153.24. The cutoff is 7.814, so at the 0.05 level significance we're going to reject, and I find the cutoff using R command Q chi-squared 0.95, and then df is 3, the degrees of freedom. Okay, so that's the show for today. I hope you have a great day.